which is placed in a magnetic field of strength B, we define something called magnetic dipole moment. Period of oscillations of a simple pendulum, and 2L is the distance between the two poles. Angular acceleration is directly proportional to displacement. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. We have started discussing a new chapter, Magnetism and Matter. We understood what was a bar magnet and the features or properties of a bar magnet. The most important property where we told if the magnet is cut into two pieces, there will be a complete North Pole and South Pole. So the poles of the magnet always exist in pairs. We studied what are magnetic field lines. We told they are imaginary lines. We told they don't have physical existence. They give the strength of the magnetic field in a certain region of space. And finally, we understood the properties of magnetic field lines, which were very much similar to the properties of electric field lines, except that magnetic field lines form continuous closed loops, which the electric field lines did not do. Continuing my discussion today, we will understand something called magnetic dipole moment. Again, a 2 marker which is asked in the exam, magnetic dipole moment. Let us just recall the definition of electric dipole moment, which we represented as vector P, and we wrote was Q into 2L I cap. And we defined electric dipole moment as the product of the magnitude of one of the charges and distance of separation between the two charges. So in comparison now, we will understand something called magnetic dipole moment. The entire chapter is an analogy, comparison between electric phenomena and magnetism. So in analogy now, we define something called magnetic dipole moment. Now I consider a bar magnet where the poles always exist in pairs. ನೆನ್ನೆ ಕ್ಲಿಯರ್ ಆಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಂಡಿದ್ದೀವಿ. Wherever there is a bar magnet, the poles will always exist in pairs. So this is the North Pole and this is the South Pole. And both the poles are separated by a distance what I call as 2L. So 2L is the distance between the North Pole and the South Pole of the magnet. Now, magnetic dipole moment is again defined as a product, as we defined electric dipole moment. Magnetic dipole moment is also defined as the product. Product of what? Product of the pole strength of either of the poles. Pole strength. It is the strength of the pole to attract iron, nickel, cobalt, etc. And we told both the poles will have the same pole strength. So it is the product of the pole strength of either of the poles and the distance of separation between the poles, exactly as we defined electric dipole moment. It is the product of the pole strength of either of the poles. Both of them have the same pole strength and the distance between the poles. And therefore, mathematically we write magnetic dipole moment is Qm into 2L, where now Qm is the pole strength. Electric dipole iddaga it was the magnitude of the charge. Here it is denoting the pole strength, and 2L is the distance between the two poles. And I put a unit vector I cap so that it becomes a proper vector representation. So now we have magnetic dipole moment, which is the product of the pole strength and the distance of separation between the poles. Now, important to note that magnetic dipole moment is a vector quantity. Magnetic dipole moment is a vector quantity, and if you observe, the direction is from the south pole to the north pole. Electric dipole moment is directed from the negative charge to the positive charge. Magnetic dipole moment is directed from the south pole to the north pole, and its SI unit is ampere meter square. So just to recollect, what is magnetic dipole moment? It is the product of the pole strength and the distance of separation between the two poles. It is a vector quantity, very important, directed from the south pole to the north pole, and its SI unit is ampere meter square. Now, the next concept, again an important one, expression for time period of oscillations of a magnetic dipole. First year syllabus we derive expression for time period of oscillations of a simple pendulum. Now, on the same treatment, I am deriving an expression for time period of oscillations of a magnetic dipole. Parikshanale, this is a very, very important 3-mark question. Time period of oscillations of a magnetic dipole exclusively based on simple harmonic motion. Now, I consider a small magnetic needle. So this is a magnetic needle placed in a uniform magnetic field of strength B. So B represents the strength of the magnetic field in which the needle is placed. The north pole of the needle, the south pole of the needle, and therefore I say it has a dipole moment vector M. So this needle has a dipole moment vector M and moment of inertia vector or I. Here I is not the current. Please do remember, I represents the moment of inertia of the needle. So my considerations are pretty simple here. A magnetic needle, observe students, this is the magnetic needle which is placed in a magnetic field of strength B. M is the magnetic dipole moment. I is the moment of inertia of the needle. Theta is the angle made by the dipole moment with the magnetic field. So, the dipole moment is defining some angle with the magnetic field, what I call as theta. Now, there is a torque which acts on the needle and oscillates the needle in the magnetic field. Or I can say, because of the magnetic field, there is a torque which is acting on this needle, and exclusively the needle oscillates because of the torque. And we know the torque acting on the needle in a magnetic field is given by the expression tau equals mb sin theta. So the expression for torque acting on the magnetic needle in the magnetic field tau equals mb sin theta. Now, dear students, can you recall any expression relating torque and moment of inertia? First PU, rigid body dynamics. We know that tau equals I into alpha. The relationship between torque and moment of inertia, tau equals I into alpha. And what is this alpha? If you remember, it is called angular acceleration. Alpha nen karidvi angular acceleration, which is denoted by d square theta divided by dt square. d theta by dt, angular displacement. Double differentiation of that should give you acceleration. So d square theta divided by dt square is alpha, what we call as angular acceleration. Therefore, the mb sin theta is I d square theta divided by dt square. This is nothing but substituting for torque, where we told tau is I alpha, I d square theta by dt square. So I am substituting for torque in equation 1. And very clearly, the negative sign shows that torque is opposite to displacement. Now, if theta is very small, assuming that the angular displacement theta is very, very small, sin theta takes up the value theta. For small values, sin theta and tan theta becomes approximately theta, and cos theta takes up the value 1. So sin theta approximately becomes theta, which means, therefore, on simplifying, d square theta by dt square is minus mb divided by I. Now I want you all to just analyze equation 1. d square theta by dt square is acceleration, which is proportional to theta, which is nothing but displacement. So acceleration is directly proportional to displacement. And that is one of the features of simple harmonic motion. So the oscillations of the needle in the magnetic field is simple harmonic in nature. Why? Very clearly, equation 1 is describing that. Angular acceleration is directly proportional to displacement, and that is a feature of simple harmonic motion. And therefore, substituting, we have T is 2 pi theta by m, or this is I divided by mb, and this gives the relationship for what is called period of oscillations of a magnetic needle. Now, trying to arrive at the potential energy of the needle, potential energy is integral tau theta into d theta, integral of the torque acting on the magnetic needle is giving us the potential energy. So substituting for tau theta, that is mb sine theta. Magnetic dipole moment, strength of the magnetic field B, they are constants. I take outside the integration symbol. So integral sine theta into d theta, which is minus cos theta. Illi nodi, cos irodrinda potential energy can be defined as a dot product, because I have the cosine of the angle here. So potential energy is minus vector m dot vector b, cosine of the angle between vector m and vector b. Therefore, it is the dot product. Again, a very, very important law, often asked for 2 marks. This is Gauss law of magnetism. Now, velladru Gauss law of electrostatics nelpiskolana. Good. Yen heltado? Total normal electric flux across a closed surface in vacuum is 1 by epsilon naught times total charges enclosed by that surface. Now, adakke compare maadi ivattu Gauss law of magnetism nodana. ಎಲ್ಲೋ ಒಂದ್ ಕಡೆ ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಅಂದ್ಮೇಲೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಲಿಂಕ್ ಆಗಿರ್ಬೇಕು. ವೆನ್ ಐ ಸೇ Gauss law of magnetism, it has to be associated with magnetic flux. Now, the statement says the net magnetic flux, where again, through any closed surface is zero. Again, if you consider a closed surface, the net magnetic flux across that closed surface should be zero. That is, B dot delta S is always equal to zero across a closed surface. So, Gauss law of magnetism says the magnetic flux across any closed surface is zero. Why is it happening? Here, all the magnetic field lines which enter the surface is equal to magnetic field lines leaving it. The lines, magnetic field lines, whichever magnetic field line will enter the element of the surface will leave the surface, come out of the surface, hence magnetic flux is zero. So, very clearly we have understood from Gauss law, the net magnetic flux across any closed surface should be zero. Why? All the magnetic field lines which enter the surface will also be coming out of the surface. So in today's session, students, we have understood the meaning of magnetic dipole moment, expression for time period of oscillations, potential energy of the needle, and Gauss law of magnetism. In the next session, we will understand the magnetism of the earth. Until then, have a good time. Thank you.